All right. Hello, everyone. Thanks for joining the session. I'm Yash. I work with the Photos team at Google. Today, I'll be discussing a case study on how leveraging a right set of metrics can help you solve a wide variety of problems related to managing your applications in Kubernetes, and how we built an internal tool that helped us achieve the same at a planet scale. So, as we know, Kubernetes provides several configuration constructs like limits, priority classes, jobs, cron jobs, etc. The idea is that the developers can optimize their infrastructure with these constructs based on the requirements that they have or the uses that they may have. Now, setting them one time is fine, but as you know, use cases change, customers and the patterns change, nothing remains the same. Meaning this often becomes like a ongoing effort, and in essence, these optimizations do take a lot of analysis of data, time, re-architectures, and often they are a big investment of your software engineering bandwidth. So because of that, more often than not, these optimizations end up taking a backseat. First, because of these fast-paced CI/CD models where you need to get something out to your customers. But once you have reached your customers, there are hundreds of thousands of metrics and even more data analysis to be done. So that is one big problem that you already have. And with no insights like maybe performance or cost savings possible, there's even lesser motivation to do so. Now, suppose despite all of that, you do want to invest in optimizing the things that you may have. The real challenge occurs when you have a large organization, like you have several independent products in different stages of your life cycle. Hence, the kind of optimizations that are relevant to each of these products would be different. As an example, if you have a wide global product with good revenues, you would naturally tend towards maybe investing your crucial bandwidth in something like latency and replication optimizations, but not something very invasive like maybe entire re-architecture into serverless, even though that may still be relevant. On the other hand, maybe a early stage POC product would be interested in both of these, but at the time, they don't have enough bandwidth to do so. Separately, a lot of commonly used optimizations may end up being done by both of these kind of teams, and unless there's a perfect cross collaboration and the things have been done in a generic way, they are reusable, it will almost always be a waste of effort and bandwidth as well. And of course, there's almost never a case where you have perfect coordination among several different teams. So that is one part of the problem as well. You sometimes have maybe some kind of optimization like QoS or priority class implementation where you need to consider a lot of, in fact, almost every other application that is present in the system because they are related terms. So it needs another coordinated effort, and it's still a difficult task to do. Now, for all these challenges, what if there was a common platform that can do this for repeated heavy usage of data and analysis for us? And it can provide some kind of recommendations which may be specifically useful for the application owners which are going to be taking actions on them. The only thing that the teams would have to do is focus on evaluating these particular recommendations and implementing them if needed. A win-win, right? So this is exactly what we built. We built an intelligent platform that can solve this at scale. The idea was that this platform can offload in fact, most of the data collection, processing, and analysis that is there from the participating teams, and all they have to do is deal with minimal changes that need from them. The idea is that it could generate some kind of predefined optimizations using these collected metrics, and the expectation is that it could be something like modular, where if you have more such customizations and more such logic that needs to be added, it can be added in incremental things as well. So how did we build it? Well, let's build together right now. So the first thing to build this we need to know is what exactly you want to optimize, right? So in your own analysis of different products, several teams, we observed that there are broadly two categories of optimization that people look at. First is governance, where you are looking at something like identifying right maintenance intervals for application, detecting anomalies, maybe determine the importance of the application, considering other applications as well in system if you have a shared infrastructure. And the second type of automation are performance and cost, which are more local to your application, like right sizing, maybe selective application, finding serverless candidates as we discussed. So these are second type of the ones. Now, all of these individually look very different problems to tackle on their own. But are they really? So what if I tell you that all of these can be solved using maybe right set of metrics and data? As an example, if you see a repeated spiky CPU usage pattern in any application, you know very well there is some kind of a seasonal pattern in this. And this application could at least very well be evaluated for serverless, running as serverless. At the same time, it's very easy to detect anomaly if there are repeated deviations from the patterns. Like, as you see here, there was a temporary offboarding of a large customer, and we see a clear changes in the metrics as well. Now, obviously, these metrics are very tailored, and they are not always going to be this intuitive. So, the reason being because sometimes these patterns have variance, they differ across different kind of resources, they sometimes have correlation with different applications that are being interacting with maybe across different clusters as well. And since we are building a platform, the first thing we should do right now is to ingest and process data as the very first and the basic thing. So we start by ingesting the resource utilization data. The one option is to do it with Prometheus using remote write to a time series database, something like timescale DB or something else. The only application changes that are needed from the teams are any custom metrics that needed to be made in the code. And you get a time series data like this. All you have to do is add the metrics that you want to get. And of course, one thing to note is that we can add as many different type of metrics that it makes sense. And it is just going to be a matter of adding one extra collector for any new metric type later. So that is the first ingredient, that is resource usage. The second thing that you would probably need is something like network interactions. So what we do is basically use the distributed tracing using open telemetry with Jigger backend. What it gives us is some kind of network traces of all the services that are interacting with what is the count, what is the latency, and if there are any custom spans that need to be added, they can be added as well by the application developers in the teams. That is the only changes that are needed from them. What we effectively get is a complete span of interacting applications across the board with latency information, errors, error rates, and all that. Yesterday, there was a talk by Steve Flanders where he talked in great detail about all of this. I suggest taking a look at his talk if you need more information on how open telemetry can help you achieve the same with best practices, pitfalls, patterns, and all. But for our purposes, all we need is this particular interacting span of applications. Now, once we have these two broad different network and resource metrics, then comes the main recipe. How do you build the intelligent logic to use this data? Now, as you would expect, each of these, this optimization is going to be different. So the logic of these optimizations is going to be different as well. So what we have is some kind of, we call it recommendation engine, where each of these engines would be focusing on very specific type of optimizations. And it looks something like this. So as you see here, we have different applications, and we have collected data from different applications and processes them. The next step is a series of recommendation engines for each type of optimization. As you can see here, we have service recommender, we have priority class recommender as well, we have node defragmentation, right sizing, and so on. Each of these engines is responsible for processing relevant data, performing very specific set of steps in the algorithm that it may have to generate this recommendation. We will see a couple of examples of that as well. It is going to be then focusing on targeting the specific applications and the user that are going to be the ones taking the actions on them. And if there are any alerting that is needed, it is going to be customizable as well. So let's take an example of processing right now. So going back to the use cases, let's say we're interested in figuring out maintenance windows and maybe checking if there are any serverless candidates in our system. So we first detect trends and seasonality. We model the resource utilization metrics using a dereferencing model. It's called seasonal ARIMA, which is a common mathematical pattern to extract the trends and seasonality from a time series data. Once we have this, we mathematically model the spikes for verification, like whether the spikes are significant or not, are they just one time or something else. And once we have this, we try to divide the times intervals into active and inactive, if that makes sense. Uh, we do it for one resource, and then we repeat it for several other resources as well. And a collective overlap across all the resources that we have is determined. Now, you may ask, why do this? That's because maybe if your application performs some kind of reads, followed by some processing and then some writes, you would see the spikes in maybe network ingress before, followed by memory spikes, and then followed by maybe disk write spikes as well. And this also helps us eliminate a lot of incorrect candidates as well, like certain resources that do not show any expected spikes can be maybe one-off something else as well. One important thing to note is that we don't try to overfit things. In this example, first one here, we just have one-time spike, but in the second one, we have repeated spikes at reasonably consistent intervals, and we filter only those. Once you have this, we have potential options for these low usage intervals. Like for example, if the utilization is negligible, the entire invocation could be skipped. Like maybe use serverless in this intervals with no invocation. And maybe if the utilization is significant, you would maybe scale down the resources to certain values which match the utilization at that particular time interval. Or maybe this could be a good time for doing any maintenance that needed as well. Once we get that, we have two different types of recommendations that we get. One is downtime recommendations, where it tells you if you want to introduce, let's say, a 30-minute downtime in service A, what are all the dependent services which are going to be impacted as well, considering all these four? And what is the best suited time interval that is good for performing any downtime on this, considering the minimal impact across all the four span of applications. Similarly, we also get something of a limited execution recommendation as well, where it tells us if certain deployments can be moved to serverless or with reduced replicas, and how much cost you would save in terms of allocated resources on these particular applications if you choose to get these recommendations implemented. Let's take another example as well. Let's say you want to see if you can reduce latency and replication costs together. So what basically we're trying to do is we are trying to figure out which all nodes are relatively close to each other in terms of network, so that you can only replicate only in those 3 or 4 different groups that you have, rather than replicating it everywhere, which may be good in certain aspects for high availability, but beyond a certain point, it may not be necessary. Why? Because obviously replication has a cost to it, but some other times we may realize that replication is not really possible in certain cases. Like for example, if you have data plane applications, you may have compliance regulations, data residency rules. You could not replicate in certain regions. Data cannot go to certain regions as well. Some other times you don't know where to replicate. The more important problem, like sometimes you have network barriers which are well beyond the common examples like geographical regions. Sometimes you have across data center latencies as well, which are significantly high. So what we do is we aggregate the latency data that we already have. We group them by node pairs, and this gives us an estimate of the historical average latency that exists between these two nodes whenever containers have been historically interacted in them. We obviously use some kind of data analysis techniques like exponential smoothing to make sure that the data is valid and in a good prepared way to use it. And once we have this, we are now in a position to group the nodes. So it effectively becomes like a graph problem where you need to group the nodes with least internal edge weights, where edge represents the network latencies. And obviously there are several different possible solutions, like one here where you just try out all the possible group sets from each starting node and set the best one which has least internal and highest external weights. So once you have these things present, we get 2 different types of recommendations. One is obviously the group sets. We you get like things like group 1, group 2, group 3 here, which is all you need to is sufficient to replicate the services, and you still have the same or effectively not a whole lot of performance hit in your applications. And also some kind of smart recommendations, like as an example here, moving pod maybe one from nodes 1 to 7 to just 1, 4, and 8 will help you save some, let's say $15 here, and still have a positive latency impact. What? Well, let's understand this with an example. So let's say if we have 3 different network distinct groups, and interactions are like this. In this case, if you observe closely, let's say if we have to replicate the service C in all the 3, obviously you will save a lot on latencies here. But if you instead migrate this workload C from the middle network group to the first one, you would still save a lot in the network time. And this is despite increased duration of calls that would be there from the third group. So if you do a quick calculation, you will understand that currently the total amount of latency per hour is 250 times 300 plus 90 times 100. And if you move it to maybe the first group, you would have just, I think, around 6,900 times 600 milliseconds of latency as well, which is still lesser than what you would see in this current example. And you're still saving a lot compared to maybe if you were moving to replicating the service in all the 3 different network groups as well. Now, this is all enough theory. How does it work in real world, right? So we made this available to about 20 different teams with several clusters. We had, I think, close to 900 nodes. We had close to $1 million of spends. We had 1,000 plus pods and maybe around 100 Kubernetes services as well. We only considered, I think, 10 standard metrics. And what we observed were something like this. So for network applications, one of the teams, which was testing infra team, got the recommendation to reduce replications across the 3 zones that they were using. They did some evaluation and settled on some custom fix where they reduced the replication and maybe resulted in around 5% of cost savings, which was around $230 per month. For the serverless refactor, our platform, as we discussed, identified around 19 services out of those 100, which had predictable spike usages, and 5 of these were recommended for serverless. One of those teams did some evaluation, and they reduced the replicas from 10 to 6 instead of moving to serverless because they were a big footprint team already. Another team, which was the interesting one here, we had a POC stage team where they were building the product, and they had very specific less number of, they didn't have a proper launch yet. So they actually were able to re-architect their application as maybe a custom or hybrid between serverless and server applications. Like they had a tenant-based serverless Kubernetes jobs that was invoked for every customer. It was a batch processing job. They also kept full-scale deployments, but with a reduced number of instances. It was 25 earlier. They moved it to 15, and now it is just 3. They needed this one because they still wanted to have ad hoc requests. And of course, if there are any customer support requests that are ad hoc, you don't want to start the batch jobs. It takes a while to bring up all the things. So they did that, and they resulted in around $3,200 of savings per month as well. And as another benefit, they saw 15% lesser container failures and restarts across all other services. That was because now the application had more headroom, more limits were not consistently being met, especially in maybe the compressible resources like CPU. We had lesser restarts as well. And we also observed, in addition to the results, some unexpected happy surprises as well. So one of the teams realized that they were having a per minute CPU spike in one of their control plane pods, which was not expected. They evaluated and realized that the liveness check that they were using in one of the pods were actually a very CPU-intensive API, which went undiscovered for a long time. And another infrastructure DevOps team, while trying to defragment one of the E2E clusters, found that the cluster that they were using was going through very frequent cycles of nodes, addition, deletion, and pods as well. And as a result of that, the Kubernetes scheduler could not optimize the placement of pods as effectively as it generally does. It led to a situation actually where a lot of memory-intensive pods were getting scheduled together, causing a resource starvation on some nodes. So they opted for something like custom rescheduling using pod affinities. They got, I think, around more than 1.5% on improvement on the throughputs, as well as around 5% lesser cost because they did not need to use as much capacity as they previously were using. How they did it, this preemptive scheduling, I have given a talk on this. I have linked that as well, if you'd like to know more about it. But the idea is basically you dynamically reschedule the pods across different nodes if you see there's such kind of a situation that is coming up. And as the last thing, we did leverage a lot of LLM help in several aspects of generating these recommendations. One such example is generating the mathematical modeling of Spike, which I have added a small snippet as well of how the prompt looked like. We also generated the AI guidance for the teams that are owning these applications if they want to add any custom spans, metrics, and how to export that. And of course, in that, the excellent documentation that we have for the CNCF products like OpenTelemetry helped a lot. And with that, we were able to help a lot of different teams that we had in the system, and without any burden on experimentally evaluating all of this information from all of those teams. So that's all I have, and if there are any questions, I'll be happy to answer them. There's a question.
Thanks for your sharing. Could you explain the underlying algorithm to detect the spike with the collected data, with the collected metrics?
Yeah, let me go back to that.
So is it a time serial algorithm or just use the LLM? Yes.
Yeah, so basically it's, we identify if there are any kind of spikes in the resource utilization data. So for that, we try to understand the moving average that is there for a resource that you have right now. And of course, that moving average would, for a short period of time, would deviate a lot. So if you have a very short period of time where the moving average is changing a lot, so we have a global moving average and we have a local moving average. Kind of what we do in maths, right? Like local minima, you create the derivatives and figure out if there's a sudden change in the derivative value of that particular mathematical function, like time series analysis we do. Same thing we do here. We have a time series data for the resource utilization metric that you have. We figure out if there's a sudden spike using the value of local global average. Local average is much more than the global average that we have. And the global average also is not changing a whole lot during the entire life cycle, because in that case, it would be a trend.
Okay, it sounds like a model-free algorithm. We don't need the data set to train the model, right?
Yeah, so that, I think I got a question. So basically, you're trying to say if you use different models, your response will be different. Is that what you're trying to ask?
Do we need to train the models like neural network or large language models to detect the spike?
Oh, no.
Or we just use the time series data like moving averages?
Yeah, we didn't use LLMs for actually doing this particular mathematical modeling. We use regular mathematical models that are there. We did use LLMs to invoke this mathematical model instead.
Okay, thank you.
Yeah. Any other questions? Going once, going twice, and sold. Thank you everyone for your time, and have a rest of the amazing conference. Thank you.